All right, guys, we're going to talk about Coulomb's law. All right, the nice thing about the unit this year is that we're not going to be doing a bunch of calculations with it, but I want you to be exposed to the actual law and see how we can mathematically understand it if we made some changes in it. So this is about electric force times a constant, that's a K, sorry, and Q1, Q2, sometimes these are lowercase, doesn't make a difference. A over R squared. Sometimes that's a D, it's just the distance. All right, so this is what these things represent. Okay, just like anything we've done in the past, we have a capital F and a subscript. It's a force. Subscript E tells me it's electrical force. All right, so it's the electrical force that is being felt between two separate charges. All right, so that's the electrical force. This, and many times in problems, in equations, you see a K that represents a constant. So it's a constant, and it's times 10 to the ninth. There's a bunch of units, but for the sake of this year, we're not going to touch on those units. But it's 9 times 10 to the ninth. It's a big number. The Q1 and Q2 are two charges. All right, so we have a value in coulombs for each of these charges. They could be positive, they could be negative. All right, and we go right back to our fundamental rules of charge. Like charges will repel each other, unlike charges will attract each other. So if these are both positive, it'll be a repulsive force. If they're both negative, it'll be a repulsive force. But if one is positive, one is negative, this will have a negative force, and that negative tells me it's attractive. All right. So just keep those two things in mind. And this R is the distance between charges. All right, so we have two charges laid out. What's that distance? That's what R represents, and it's a squared value. All right, so that's what all the different variables represent. Okay, the electrical force equals the constant times the charge of charge 1 times 2, and divided by the distance between the charges squared. All right, so that's what those things represent. Now, what I'd like you to be able to do, and in class we went over actually plugging numbers into each of those things, and putting in our calculators and seeing be a really small number. There's a lot of scientific notation involved, which can just be cumbersome. It's not hard necessarily to solve for these things, but there's mistakes to get made constantly in plugging it in the calculator. We're going to kind of avoid that this year and just try to see, and I think build a good skill mathematically. If we made a change over here, how does this affect something over here? All right, so this is how we do it. The way that I like to explain it is, all right, we got a fraction over here, we got a quotient bar. All right, so what I do is I put a quotient bar on the other side. Whatever I do on top, I do on top. Whatever I do on bottom, I do on bottom. And that's how it affects my electrical force. So this is what I mean. If I said, all right, we don't even know the values of any of this, but we can still figure out the relationship. If I double the charge of Q1, I put a 2 in front of it. Well, there's a 2 on top of the quotient bar, so I just put a 2 on top of the quotient bar. And there's nothing underneath, so like any fraction, if there's nothing underneath, it's over 1. So if I double the charge of 1, I'm going to double the overall force. But what happens to the overall force if I double both? Okay, this is all multiplication. 2 times the charge times 2 times the charge. The order I do this in makes no difference. So 2 times 2 is 4. There's still nothing on the bottom, so it's over 1. So doubling the charge of both, my electrical force will increase by a factor of 4. It'll be 4 times greater. All right, hopefully that makes sense. If I put a 3 here, it'd just be 3 times 2, it'd be 6 times. If I put a 10 there, it'd be 10 times 2, it'd be 20 times. Okay, whatever you do, just multiply it and put it on top. Pretty straightforward. All right, on the bottom, we have a squared value here, so we have to keep track of that. All right, let's erase these other charges. All right, we'll use a different color. All right, we'll say, all right, what happens if I double the distance. All right, so we had they were this far and I doubled the distance. Now it's this far, it's further away. The further away they get from each other, the less force they're going to feel between the two of them. All right, so I should anticipate that this number will go down. It'll get smaller. All right, and so it's 2r. Now I got to square all of that, and that's where the mistake gets made many times. They just say, "Oh, put a 2 on the bottom, done." No, we got to square it because we've doubled r, so we square all of it. All right, so that means 2 squared is 4. I'm on the bottom. Put a 4 down here. Nothing's on top. I put a 1. Okay, if I double the distance, it's going to be 1/4 the original value. All right, so what happens if instead of doubling it, I triple it? Okay, I tripled it. Exact same thing happens. 3 squared is 9. It's going to be 1/9. Right? The further I get away from it, the less and less force it feels between those two charges. Maybe I can also, what if I said I'm going to double this charge and I'm going to double that charge? Okay, great. Now, 2 times 2 is 4. The overall charge would be 4/9 of the original charge. So that's all you do with this. That's all I want you to be able to do. Whatever happens on top, put on top. Whatever happens on the bottom, you put on the bottom. All right? So it gets smaller the further you get away. That makes sense. All right. Hopefully that seems pretty clear. We could change these numbers to whatever, and it would just affect this by multiplying whatever those are. 2 and 4 would be 8, so put 8 over there. 4 would be 4 squared, and put 16 on the bottom. Okay, whatever change, you just make sure you do it on both sides because it's an equation, so it has to do the same thing on both sides to remain true, to remain equal. All right. Now, so remembering to square that value is a point that people forget. All right, I'm going to change. We're going to try a couple more problems here. Because what happens if instead of increasing the distance, I decrease the distance? All right, so instead of, I had 2 charges that are this far apart, what if instead I move this one to be half, so now it's closer? Well, now we're taking 2 things that are feeling a force between the two, maybe repulsive, maybe attractive. The closer I get to them, the greater that force they're going to feel, the greater that interaction they're going to have between the two. And so I should anticipate that this number is going to get bigger. But, I put a fraction. Let's say it's 1/2 here. Well, fractions seem to get smaller. So how is it actually going to get bigger? Well, let me show you here. It's just your basic arithmetic. All right, have your quotient bar. Same thing. Remember, just like before, it's 1/2. So 1/2 squared. Okay, I would put 1 over 1/2 squared. You might look at that and be like, "That I hate fractions." Now I got 2 fractions and an exponent. All right, let's simplify things here. All right, remember, 1/2 squared is equal to 1 squared over 2 squared, which is 1 over 4. Remember, squared is just 1/2 times 1/2. I go across, 1 times 1 is 1, 2 times 2 is 4. All right, so this is equivalent to 1/4. So that seems a little bit less messy. But I got 1 divided by 1/4. Divided by a fraction, it's intimidating. Okay, well, let's just go back to our math here. If we have 1 divided by 1/4, okay, 1 is the same as 1 over 1. How do we divide 2 fractions? Right, we take the reciprocal and multiply. So this is equivalent to 1 over 1 times 4 over 1. So now this is actually 4 times greater. All right, so there's a lot of steps here. Some of them you may feel like, okay, I get that. Some of this may be a quick review for you. Okay, but if I get it tighter, get it closer together, the force is going to increase. Okay. So what if I did a third? So now it's even closer. Even closer. All right, if you go through the whole thing, it's like 1 over 9, because 1/3 squared is 1 squared. 3 squared is 9, 1 over 9. All right, 1 over 1, a divided by 1 over 9 equals 1 over 1 times 9 over 1. So this would actually be, this is equivalent to 9 times. So this is a point that can be a little bit confusing. Remember, to square it can be a little bit confusing. If I double this and did that, it'd be like 2. So it'd be 18 times greater force then. Okay? Stuff stays on the top. This, because it's a fraction, gets flipped to be on the top. And then if I double this, it'd be like 2 times 2. That's 36 times greater. So there's a lot of different ways. I just want you to be able to kind of mathematically work with this a little bit, feel kind of comfortable. You'll do a couple of problems like this on your test next week. And so be sure that you get a little bit of practice. I think worksheet 3 has, I think, 4 or 5, actually, I think 8 problems like this with some numbers and give you this value and just say, all right, if it's 2 times that, if this was 5, 2 times that, the total force would be 10, right? It's in newtons because it's a force. All right, so any questions, make sure to reach out and let me know. Hopefully that clarifies.